Hi, this is Gaurav Krishna. Today we'll solve one of the most challenging problems in mathematics, that's Collatz conjecture. Now, a lot of people have tried it and found it very difficult to solve this problem. Let's give it a shot. Okay, so now what the conjecture states is if a number is 0 mod 2, that means it's even, we apply the rule n by 2. If a number is 1 mod 2, that means it's odd, we apply 3n plus 1. Pretty simple, straightforward, no complications. And now the conjecture states that eventually every number is going to reach 1. Now let's take an example. Let's take the number 7. Because it's odd, we apply 3n plus 1. What we get is 22. 22 is even, we apply n by 2. We get 11. 11 being odd, 3n plus 1. We get 34. 34 even, apply n by 2, we get 17. When we apply 3n plus 1 on 17, we get 52. Now 52 is going to be divisible by 2 twice, so we apply n by 2 twice and we get the number 13. And we keep on continuing the process and we eventually end up with 1. Now let's take the set of all natural numbers, a universal set, that's u. 1 2 3 4 5 6, all the elements are there. So it has a lot of even elements like 2 4 6 etc. What we do is we apply n by 2 till we get odd, so we are left with the set 1 3 5 7 9, so on and so forth. Now this set contains only odd elements because even have been eliminated. Now let's call this set as u prime. Now we are not really going to be concerned a lot with the set u. Our focus is just going to be on u prime. We will realize eventually that even numbers are of no consequence whatsoever. We are only going to be interested in studying odd numbers. Now let's take the set of all odd numbers, that's u prime. It has all the odd numbers. Now we start defining sets. Now the thing is that we are not really going to be attacking the problem straight away head on. What we will be doing is we are going to define sets like ry, rv, etc. and we are going to study the properties of these sets that we define, how they behave, and then test the conjecture if it's true or false. No direct attacking, we are going to have an indirect approach. Now ry. Now r0, r sub 0 is exactly the same set as u prime, no variation whatsoever. This is by definition. Now let's define the rule when y is odd. Okay, now when y is odd, we will apply the rule r y minus 1 plus 1 by 2. Now say r1, 1 is odd, the rule is going to be, say, let's take the number 3. Okay, now what we do is we want 3 and we want to next number from 3. How do we do? What do we do? We take ry minus 1. This is ry minus 1 because this is r1. r1, I mean y minus 1 is 0, so we look at this set. So we have 3 plus 1 is 4 by 2 is 2. We have the number. Similarly, you can take the expansion for number 5. You have 5 plus 1 by 2, it's 3. 6 by 2 is 3. So this is the way we create our set r1, and then now we expand. We first of all define the rule for even y. For even y, the rule is r sub y minus 1 minus 1 by 2. Only slight variation. Here we have plus 1, here we have minus 1. Now let's define the set r2. Now there is one thing that we need to keep in mind. We are not going to be expanding these even numbers. If for any value we get an even number, we would not be expanding these even numbers. We will only expand till the number is odd. Okay, so we have the number 3. Now what we do is 3 minus 1 is 2, divide by 2 is 1. We get that value. 5 minus 1 by 2, we get 2. So this is the way we create our set r2, and we have r3. Again, it's odd, so we use the rule for odd. Y, we have even, r4, r5, r6, so on and so forth. It's not very complicated. What we're doing is we will keep on expanding. Say you have this number 21. Now we keep on expanding till the value of r is odd for any given set. We don't really care about the value of y. We are interested in value of r. R is when I write the formula, ry is equal to ry minus 1 plus 1 by 2. what I am going to be doing is I will be playing with the value of r. Okay, now we can keep on expanding till we get even elements. Okay, a small demo. Now we define the set RB. RB is exactly the same, just one thing. Now say you have R1. In R1 we have the element 2. So because 2 is even, we are not going to be expanding it further. So we define RB. Okay, so it is RB where B is equal to 1. We have 2, 4, 6. These are the elements of this set. Now these are the elements. They are related to the number 3, 7, 11 and so on. Okay, now say we are talking about RB when B is equal to 3. Okay, now when B is equal to 3, our first is 2. Now 2 is for element 13. So when RB is equal RB such that B is equal to 3, we are talking about the element 13 and the value for R is 2. So you write 2 sub 3 in terms of RB, and it is related to the element 13. So what we are doing is we are basically mapping all these elements to various sets of R. Now it can be B ranges from 1 to infinity. It can be however large it's possible. We will keep on continuing till the value for R is odd. Okay, and when we apply 3n plus 1, these are the values that we get, all even values, and then we can apply n by 2 multiple times, 1 or multiple times depending upon the requirement, and then we get certain values. Now let's define nx. Nx is a preceding element and ns is next element. Say you have the number 5. Okay, now for 5 the preceding element can be 3. When you apply 3n plus 1 on 3, you get 10, and you divide it by 2, you get 5. By default n by 2 is going to be inbuilt in our calculation. We are not really going to do it separately. It's not going to be a separate mechanism. It is going to be a part of transformation. Now by transformation I mean from moving from one odd element to another odd element. Whatever even element lies in between, we don't care. We are not concerned with that. Okay, x is x, your x. S is spouse, that is your present. Okay, that is the way we define this. We understand it. Okay, now the thing is, the language of the paper is a bit formal, like you have a lot of symbols over here, but it's actually very simple. If you understand these symbols, it's walk in the park, nothing else. Now for all nx that are subset of u prime, there exists rb for sub nx, which is a part of rb for b is equal to 1 to infinity, such that you have these rules. 3nx plus 1 is equal to ns into 2 to the power b. So here, if you see, we consider nx and ns both to be odd elements because we write 2 to the power b. And so whatever is the divisibility of the element, like in the previous slide, if you go, if you think about it, we mentioned b. It is the same b, exactly same b. And nx and ns are 2k minus 1. They are odd. K, b are a part of positive integers. Now this statement essentially means that there does not lie any element in the set u prime which does not have an associated representation in the set rb. Okay. Now what we are going to do is we are going to study the number of elements of all these sets. Okay. Now say you have set R1. Number of elements in R1 are half of the number of elements in u prime, that is R0. Number of elements in R2 are half of the elements of number of elements in R1, which is equal to 1/4 of the number of elements in u prime, and so on and so forth. So how do we know that these are half of the elements? Because what we do is we are expanding only the odd elements, and it's safe to assume that half of the elements are odd and half of the elements are even. So in any given set, when you have 1 2 3 4 all these numbers mentioned, when we expand only the odd numbers, so we are expanding only half of the numbers. So only half of the numbers have a representation in the next set, say R1 to R2, you have just half of the numbers representation. Now if we consider the total summation of all these numbers of all the possible sets of RB, what do we get? We get 1 by 2, that is the number of sets, 1 by 2 of U prime, 1 by 2 to the power 2, that is 1 by 4 of U prime, and then again half, we keep on adding 1, we keep on multiplying it by 1 by 2, and this the solution for this expansion is already known to be equal to 1. So this means that all the elements of these sets RB, where B ranges from 1 to infinity, we have the summation 1 by 2 q as in the number of elements, q of U prime. Again, in terms of U prime, we have all these values, and then this is actually equal to U prime. So this basically tells us that none of the element of the set U prime is there that is not represented in any of these RBs. So if you consider all the RBs, the sum of all the possible RBs is equal to sum of all the elements of U prime. Now let's establish a few theorems before we move ahead. So by definition, RB is equal to RB minus 1, that is the preceding set, plus minus 1 by 2, depending upon the nature of B, if it's odd or even, whatever. So R1 we have R0 plus 1 by 2. R0 is exactly same as nx, that is the preceding number. So nx plus 1 by 2 to the power 1. So you do some calculation and you get it in this form: 3nx plus 2 to the power 1, 1 as in B, plus 1 divide by 3 into 2 to the power B. Okay. We take R2, we plug in the value for R1, we use our definition, we plug in the value for R1 in terms of nx, and then we get us a different one, a different formula. Here you have a plus sign and here you have minus sign. Slight variation, essentially the same. Again, you take R3, you keep on expanding in the set format. You have plus, so you have plus for all these odd numbers and minus for all these even numbers. More or less the format is pretty similar. Okay, now we can see this. Let's establish that this to be true. Now what we do is, in theorem 1 we basically just establish that the fact is true. Now I'm not going to be sharing the proof for it. If you are interested, you can look at the written paper. Okay, now for all values of nx, if RB, the RB has well-defined values that depend upon the parity of B. If B is even, it behaves in a certain manner. If B is odd, it behaves in a different manner. Okay, so the proof is there in the paper if you are interested. I just wanted to give you an overview. Now let's look back at the table that we created earlier. Okay, now let's notice something very interesting. You see, 0 plus 1 is equal to 1, 2 plus 3 is equal to 5, 1 plus 0 is equal to 1, 4 plus 7 is equal to 11, 5 plus 7 is equal to 7. We see a pattern over here. If I take the summation of last two elements, that is, one would be even and one would be odd. Okay, say you have 4 even number that is related to the set RB, where B is equal to 2, and this is RB minus 1, that is B is equal to 1. So 4 plus 9 is equal to 13. So after transformation, when you apply a 3n plus 1, okay, you get 52. You apply n by 2 twice, you get 13. So basically what's happening is, instead of applying the rule of 3n plus 1, all I need 3n plus 1 and n by 2, all I need to do is just consider the last two values of set R set RB. So this is the theorem. It says that for all RB plus RB minus 1 is equal to ns. So in this case, we have our set. Okay, now this is nx because this is the preceding element, this is the next element. Now we know that say the number 17 gives the number 13 upon applying 3n plus 1 followed by n by 2. So ns, that is ns, and this is nx. So if I do not use nx and just apply the rules for RB and RB minus 1. I can create these sets RB and RB minus 1 for nx, and I can just sum the last two. I get my solution that I get after transformation. The proof is there in the paper again. Alternatively, there is another way. We approach theorem 1, and then what we do is we plug in the values of theorem 1 and then prove this thing. If you are not interested, if you don't like theorem 1, you can just ignore it. You can just consider the expansion of RB and RB minus 1 in the form of continued fractions. And what you would get is it is equal to 3nx plus 1 by 2 to the power b. Now, if you look at our transformational law, it is 3nx plus 1 is equal to ns into 2 to the power b. So basically what I do is I take 2 to the power b from here and put it down over here. So from an odd element I get another odd element. I do not have any even element. All the even elements are encapsulated in 2 to the power b, and it just gets eliminated automatically. So what we have is we can create a function that is similar, that gives not similar, that is exactly the same as Collatz transformation. Moving on, let's start establishing a few corollaries. Let's begin with corollary 1. It states that it talks about increase decrease condition for any transformation. If b is equal to 1, nx is smaller than ns. That means nx is going to grow. If b is greater than 1, nx is going to shrink. So you will get a smaller value after transformation. The proof is again there in the paper. Yeah, one thing to note is that for ns greater than 1, these things are applicable. For ns is equal to 1, you will just get 1 every time. So this rule is not applicable over here. Okay, now corollary 2. Corollary 2, we have R1s, that is R1 for ns is equal to 3 by 2 R1 for nx. So earlier we established that it is going to increase. So we know it is going to increase because b is equal to 1 as defined over here. But increase, now here we are talking about the rate of increase. We know precisely what is the rate it's increasing. Now what is increasing? Not the value of nx, but the value of r. So we are looking at the problem and solution in terms of r, not nx or ns. Okay, now let's take an example. Let's consider nx to be 9. Okay, and you apply transformation, you get 7. You apply transform. Now for 7, if you look at it in terms of rb, you get 4 1. Value of r is 4, value of b is 1. Now when you apply transformation on 7, the result you get is 11. Again, by transformation I mean 3n plus 1 followed by n by 2. Both the things are coupled. That is one step. Okay, so from 7 you get 11. For 11, if you look at the value of rb, you get 6 1. This means that it was 4 into 3 by 2, we get 6. And if you apply transformation again, then eventually your value of b increases. Now we prove this thing using corollary 1 and 2. Now what does it mean if b increases? When b increases, that means we know that the number is going to shrink. So we know for how long a number can grow continuously. Say you have the number 32. Let me just pen it down. Pen. You have 32. Okay, now 32 is 2 to the power 5. Oh, writing is 2 to the power 5. So it is going to increase 5 times continuously, and then it is going to fall. Your resultant would be if the value of r is 32, your result will be 3 to the power 5, and this thing is going to be eliminated. 2 to the power 5 is going to be eliminated by this. So you will end up with an odd number, and the moment you end up with an odd number, that means you will have to continue expanding the set, because that's the rule of the game. Now if you expand the set, you have b greater than 1, and when b is greater than 1, it's not going to increase continuously. So we are clear about that. Now this means that if there is some transformation going on from nu1 to nu infinity, wherein nu infinity is almost infinity and the growth rate is continuous, as in n1 is smaller than next transformation, the number keeps on growing and growing and growing. If we have such a condition, if we imagine such a condition, because of corollary 1 and 2, we can establish that such a condition is not possible and it's false, because eventually upon dividing any event element by 2 repeatedly, we will eventually reach an odd value for r. And when you have an odd value for r, you will have to apply the rule for expansion, implying b greater than 1. That means it's going to shrink. Alright, but we know that it's not going to expand continuously, but here we have a condition where there is some transformation that is taking place and we don't know if it's expanding, if the number is growing continuously or not. We know that it cannot grow continuously to infinity, but it can grow for a few steps and then shrink back and then grow again. And if it reaches infinity in that way, how do we figure out? So we take a different approach. We try and imagine that a number explodes to infinity. We have our number nx explodes to infinity. So this statement 3rb plus minus 1 is equal to ns. It is basically just theorem 2 written differently. You just put in the value of rb minus 1 and then you will get this same equation. No big deal about it. Now we have ns, that is after transformation at some point you reach infinity. Okay, so it means that 3rb plus minus 1 is equal to infinity. So rb is equal to infinity plus minus 1 by 3, which is some strange notation, but we know that it basically is not an element of u. So rb is not an element of u if this reaches infinity. But by definition, we know when we defined rb was always defined to be a positive integer, and positive integer is a part of u, or same as u. So by contradiction, we realize that this proposition is false. That means a number nx cannot explode to infinity. Earlier we established that it cannot grow to infinity continuously. Here we know it cannot grow to infinity even if it's growing and falling and growing and falling, whatever. We don't care. It cannot happen. Now we have already established that a number cannot grow to infinity either directly or indirectly. Let's talk about corollary 3. ns cannot be congruent to 0 mod 3. It is basically self-evident, but it's actually instrumental in the paper, so I gave it a special place. It basically means that here what we have is 3 into some number plus 1. So this is always going to be 1 mod 3. Now 2 to the power b can be 1 mod 3 or 2 mod 3, we don't care, but any which ways ns cannot be 0 mod 3. It cannot be a number that is divisible by 3. Okay, now corollary 4. Corollary 4 says that if n1 is congruent to 1 mod 3, n2 is congruent to 1 mod 3, then the resultant is congruent to 1 mod 3. n1 into n2 is equal to n3. This is what it's talking about. Similarly, you have the condition, another condition for 1 mod 3 and another condition for 2 mod 3. So these are various conditions we establish, and we use this piece of knowledge to establish theorem 3. There is a well-defined relationship between ns modulo 3 and parity of b. Now parity of b is essential because rules change. We can determine ns modulo 3 by the parity of b and vice versa. Now what the theorem basically states is, if the value you get after transformation is 2 mod 3, then b for that transformation has to be odd. Alternatively, if b is odd, then the result you are going to get is 2 mod 3. Similarly, you have, if b is equal to even, the result you are going to get is 1 mod 3. So actually, without doing any calculation whatsoever, just looking at the value of b, we can predict what the congruence of ns modulo 3 is going to be. Okay. Now we define set nx. Nx is earlier I just introduced you to nx, but nx is not one value. Nx is actually infinite values. Nx is a set that contains all possible values of nx. that would satisfy this equation. Now this equation has a lot of solutions. Say b can have any value, right? So when b, the value of b is different, the value of nx has to be different for any given ns, right? So that is pretty self-evident. Now nx, earlier we established the rule for parity of b. Now here we have used the variable beta instead of b. Now beta refers to b being equal to 1 or 2, nothing more than that. Beta is equal to 2 or beta can be equal to 1. It depends upon ns modulo whatever its congruence is to modulo 3. Now nx, we can write this thing nx in terms of various formats. Say b is beta. Now let's assume that b is equal to 1. Okay, now you have 1 plus 2, that is 3, 5, 7. So all these numbers, b is going to be odd. If ns is 2 mod 3, if you plug in the value for any b even, you are not going to get any valid integer solution for nx. So the only way to get integer solutions is by adding 2, 4, 6 even numbers. Okay, now if it's odd, then all these values have to be odd. These values as in values of b, possible b's. If beta is 2, then all these values have to be 2. So it is basically we are just using our understanding that we developed. Say ns is equal to 5, because ns is congruent to 2 mod 3, our b is odd. Now when b is odd, we can say beta is equal to 1. So we use the same formula over here, expansion over here, plug in the values, we get this set. Now when you apply 3n plus 1 on 3, 13, 53, 213, 853, any number, you will always get the number 5. So I know all the infinite ways to get the number 5, and because b can have any value from 1 to infinity, yes, b can have any value from 1 to infinity, this set is infinitely large. Now if you look at it, there is one more interesting thing. 3 into 4 plus 1 is 13, we get the next number. 13 into 4 plus 1 is 53, we get the next number. 53 into 4 plus 1 is 213. So if I know the first solution that is related to beta, I will call this as base solution, base value for nx. If I know the base value, I know all these values. I just have to use this formula. Now earlier we noted that there is a relationship that exists. Now we will establish the relationship as in nx into 4 plus 1, giving the next value. Okay, now let's create a notation for all these values of set nx. The way we are going to do is nx1 plus 1, nx1 plus 2 plus 3 plus 4 and so on. It is not nx1, nx2, nx3. We won't really go with that format. We will go with this format. It makes sense. If you start looking at the problem in detail, you will realize this is a more sensible way to present it. Okay, so you have sum 3 nx1 plus 1 is equal to ns into 2 to the power b, whatever the parity of b may be, we don't care. Okay, now we have nx1 plus 1, so this is this solution, and here you have plus 2, that is supposed to be the second solution over here related to this. Why plus 2? We have already explained. So the parity of b has to be the same. If beta is odd, then it's going to be odd. If beta is even, it has to be even. We are just maintaining the parity. Now we expand this and we get 12 nx plus 1, and then we can solve it further. We end up with 4 nx1 plus 1. So 4 into whatever this value is, we get the same thing. If we look for the third solution, first, second, third solution, nx1 plus 2, we end up with the similar nature of thing. 4 nx1 plus 1 plus 1. So this number is equal to 4 into this number plus 1. Okay, so on and so forth. Now we create a generalized formula, nx1 plus z plus 1 for some number is equal to nx1 plus z. It's essentially the same thing that we were talking about earlier. Okay, now this is an important and interesting thing. Congruence modulo 3 is well ordered. Now because we will be using our previous knowledge to establish this fact, as in if the value of nx1 is 0 mod 3, the second solution is going to be 1, the third solution is going to be 2, and then 0 mod 3. So it's a cyclic thing, 0 followed by 1 followed by 2 followed by 0 followed by 1, so on and so forth. If nx1 base solution is 1 mod 3, then you will have the next solution to be 2 mod 3 and then 0 mod 3 and then 1 mod 3, so on and so forth. Likewise, if nx1 is congruent to 2 mod 3. So this thing, once when we establish that, this thing is going to empower us to test for loop. We have already tested for infinity. We know that it's not going to reach infinity. Now this is the knowledge that we are going to use to test if a number can possibly loop. Now say we have a solution, ns is equal to 5. So we use our formula. We have 3, 13, 53. We established this earlier. Okay, 0 mod 3 followed by 1 mod 3 followed by 2, 0, 1, 2, 1, 2, 0. You know, it just talks about the cyclic nature of things. So this formula is always going to be true for all the solutions of the set nx. Okay, and this means that 1/3 of all the possible solutions are always going to be 0 mod 3. And we established earlier that ns cannot be congruent to 0 mod 3. Now overall we are clear that for any nx, the values of nx1, nx1 plus 1, nx1 plus 2, so on and so forth are well ordered. Okay, now let's dig in further. Okay, now let's look at these numbers with respect to them being modulo 9 and modulo 27. So when we think about numbers modulo 9, so we have these combinations: 1 modulo 9, 1 mod 9, 2 mod 9, 4, 5, 7, 8 mod 9. Okay. And these numbers in terms of their mod 27 definition will have certain different values. Okay, so when you look at 1 mod 9, 1 mod 9 can give you 3 results. Their nx has 3 possible results, that is 7 mod 9, 4 mod 9 or 1 mod 9. Now these results depend basically on its value ns mod 27. So if some number is ns 1 mod 9 and it's 10 mod 27, so its nx is always going to be 4 mod 9. It is the same for other examples as well, other cases as well, not examples. So for 2 mod 9 you again have 3 cases of 2 mod 9 as in 3 definitions in terms of mod 27 and 3 different results in terms of nx mod 9. And if we move forward now, if we continue, we can look at 4 mod 9. It has 3 definitions in terms of mod 27 and 3 possible results of nx in terms of mod 9. We do this for all these cases and we get this sort of a table. Okay, now if we want, we can arrange them in terms of mod 27 as in 1, 2, 3 incremental format. But although it's just to enumerate the number of cases that we are studying, but this section does not really has a lot of bearing on the solution. Now what's interesting is if we align these solutions in terms of if we group them, say all the solutions that are 0 mod 3, how do we get it? If a number is 5 mod 9, irrespective of its value, irrespective of its definition in terms of mod 27, it is always going to have an nx that is 0 mod 3. If a number is 7 mod 9, its nx is always going to be 0 mod 3. This can be checked in the you can derive it from this table has been derived from this analysis. Now if we group them in terms of mod 1 mod 9, so how do we get 1 mod 9? We can get it from 2 mod 9, that is 2 mod 9, which is 2 mod 27, it gives 1 mod 9. 1 mod 9, which is 1 mod 27, gives 1 mod 9. Similarly, you can create definitions for other possibilities. So one thing to note is we have 2, 4, 6, 8, 10, 12 plus 6, 18 different cases. Okay, 18 different cases, out of which 6 cases are 0 mod 3. That means 1/3 of the cases are 0 mod 3 and 2/3 of the cases are something else. 1, 2, 4, 5, 7, 8 mod 9. In terms of mod 3, there would be 1 mod 3 and 2 mod 3, to put it very simply. And we began our study with 6 cases. 1, 2, 3, 4, 5, 6. So 6 cases, every case has 3 subcases and it gives you 18 results. So when you have a number that is 5 mod 9 or 7 mod 9, you have its nx to be 0 mod 3, and 0 mod 3 cannot loop. So this is going to be a key factor. Okay, now if we look at our previous study, we were able to establish that 1/3 of numbers are 0 mod 3, and here we have 1/3 of the numbers are 0 mod 3, but there is a difference between the previous corollary 5 and this table. The difference is that there, for any given nx, any given ns, we are looking at all the possible nx. Here we are not looking at all the possible nx. We are just limiting ourselves to nx1, that is the first solution, which is basically the base solution. Now this table talks about the distribution of numbers. So earlier in corollary 5, we had established that they are well ordered. All the elements of nx are well ordered, and here we know the distribution, they are well distributed. When we combine corollary 5 and this given table, we have our theorem 5, and we will be using theorem 5 to further probe in further and check if there is a possibility of loop or not. Now this is our weapon. Okay, now let's we have a proposition that some number possibly loops to itself. Now there is 2 ways it can loop. One is it transforms directly to the same number. Second, it goes through multiple transformations. The sign represents transformation, it is directly transforming. Double equivalence means it takes more than one step to transform, such that nx is not equal to ns. So this is an important condition we need to keep in mind. Okay, so let's imagine some condition for loop. You have some number ns, it transforms to some number n t minus 1x, it goes on and on and on, and then you have n2x, n1x, nx, and then ns, and this loop continues, and we have this thing, nx is not equal to ns. Now proposition 2a, if we study this, it's a we know that one of the trivial solutions is 1 transforms directly to 1. Now if we plug in the value nx is equal to ns, and then we have this sort of an equation. So for any value of ns that is greater than 1, right hand side will always give you some sort of a fraction. You have a rational solution, but this is not going to be a rational solution. We expect this to be, no, we don't expect, we know that this is going to be an integer. So integer is not equal to some rational number. There is some problem over here. So there is no value of b that could dish out a rational solution. Thus no value of ns satisfies this condition. So we know that for proposition 2a, this is the only condition where nx is equal to ns is equal to 1. Now let's start defining next set of sets. They are related to tau. Now earlier we had defined sets of RB, then we earlier defined RY, and on basis of that we defined RB, and now tau. What are these sets? These sets represent reverse transformations from our set U prime. Now we take our set U prime and then we begin with tau sub 0. Now tau sub 0 is essentially the same set barring element 1. Why? Because element 1, for element 1 we know that nx is equal to ns, and we had specifically defined in our condition that when we are looking for multiple transformations, loop via multiple transformations, we do not want nx to be equal to ns. So we remove this out of our analysis. This has to be excluded. Now let's start defining. From tau sub 0 we move tau sub 1. So this is a set that represents one transformation away, reverse transformation away from our set U prime. And while doing this we come across a lot of does not exist signs. Now why do they not exist? Because number 3 and then 9, 15, 21, 27, all of them are 0 mod 3. And if ns is congruent to 0 mod 3, it does not have an associated nx. There is no value of nx that satisfies the equation. So we cannot expand these values that are 0 mod 3, and this is going to be our key. This is going to be the weapon that we would be using to prove that loop cannot happen. Because if all the elements in set U prime at one point of time somehow reach 0 mod 3 via reverse or forward transformation, either ways, then we know that loop cannot happen. Now while forward transformation we know it's never going to reach 0 mod 3. So what we do is we imagine a case where a loop is taking place. Okay, now if a loop is taking place and then the only possible values for loop are 1 mod 3 and 2 mod 3. You cannot have any other value. You can never have a 0 mod 3 in the loop. And so if we move back, we move anti-clockwise, we carry out a reverse transformation, and if we come across a 0 mod 3 element, that means that the element cannot loop and the series is broken. So there is a stopping point. Loop means that there is no stopping point. It can go on and on. We can have infinite number of circles. So that is the key over here. Now what we do is from tau sub 0 we expand to tau sub 1, and then tau sub 2, tau sub 3, so on and so forth. Say 13, let's take the element 13. Nx for 13 is 17. Nx for 17 is 11. Its nx is 7. Its nx is 9. And when we reach 9, it is 0 mod 3. And 0 mod 3, that means there is no representation in tau sub 5. What are the number of elements that we have? Let's look at that. So you have your set U prime, you have your set tau sub 0. The total number of elements in tau sub 0 is equal to total number of elements in U prime minus singular element 1, which we have removed from our analysis because the condition is not being met. Okay, now the second thing is tau sub t for any t. It comprises of 3 subsets. That means nx. We studied earlier that nx has 3 values, 3 possible values. It can be 1 mod 3, it can be 2 mod 3, it can be 0 mod 3. So, and because it is cyclic in nature, the number of elements in this set is equal to number of elements in this set is equal to number of elements in this set. And when you combine the total number of elements in all these sets, you have total number of elements in this set. So it's like, say you have tau sub 1. Okay, let's look at tau sub 2. Okay, now you have some number that is 0 mod 3, you have 2 mod 3, you have 1 mod 3, you have 0 mod 3, you have 2 mod 3. So the set tau sub 2 comprises of these three possibilities, and all these three possibilities are in equal quantity because of the cyclic nature. Now if we are to expand from tau sub t to tau sub t plus 1, that means any element that falls in this category cannot be expanded. So tau sub t plus 1 is equal to tau sub t not 0 mod 3. So the number cannot be 0 mod 3, and the example describes how we have removed them. So tau sub t plus 1 is equal to tau sub t for 1 mod 3 and 2 mod 3. It's a union of these two sets. Alright. So quantity of tau sub t, what can that be? We know that quantity of tau sub t is basically quantity of tau sub t that is not 0 mod 3, representing this. So when you say not 0 mod 3, so you take all the number of elements in tau sub t minus 1/3 of tau sub t. Why? Because we know this is 1/3 of the total number of elements. So you subtract it by 1/3 and you get 2/3. So tau sub t plus 1 is equal to 2/3 of tau sub t. These are the number of elements that we are talking about, quantity. So we are clear about this. Now we do the analysis for, say, tau sub 1, tau sub 2, and then we write them in the form of quantity of universal set, number of elements in universal set minus singular element 1. Now earlier we noted that the set nx is a set that contains infinite values, but for deriving set tau sub t from tau sub t minus 1, we did not consider all these infinite values. We just considered the base solution of nx, and no other solution was taken into account. Does that make our analysis incomplete? Let us study that. Let's take the example. Say ns is equal to 5. If ns is equal to 5, its nx are 3, 13, 53, 213, so on and so forth. Okay. Now for ns is equal to 5, we just considered 3. We did not consider any other value. Say this is the value we considered. But for 13 that we had ignored, 13 is already being analyzed in its separate row. Similarly, all the elements, 53, 213, 853, whatever the value is, they would be studied in their own definitive row. So none of them is going to be eliminated out of our analysis. The reason for being so selective in terms of expansion is very critical. We want the relationship between tau sub t and tau sub t minus 1 to be bijective and invertible. Now why do we want that? To be able to keep track of number of elements in every set, because that is the strategy we intend to use. So before moving on, let's first take some infinite series and see what its value is. Let this be equal to s. What we do is we take the first value, put it on the right side. You have minus 1/3, and then all of them are divisible by 2/3, so you remove 2/3, and then you get this similar thing. Now because it's infinite, it does not really matter. We can just plug 2/3 into s, and we get s is equal to 1. So we know the value of this infinite series is s is equal to 1. We'll be using this later on. It's better to just finish it off before we use it. Sorry. So summation of quantity, summation of number of elements in tau sub t that are 0 mod 3 for t ranges from 0 to infinity. Okay, now that is what we intend to find out. Okay, So we know the value of all these sets in terms of number of elements of Q minus singular element 1. So it's we get this form of an expression, and this we know is already equal to S. So what we get is summation of all elements in tau sub t that are subset of 0 mod 3 is equal to, you know, from when t ranges from 0 to infinity, is equal to total number of elements in set u prime minus singular element 1. What does it mean? All the other elements of u prime which reach a value that is congruent to 0 mod 3, that means they cannot loop. So loop is not possible. So here we disprove the possibility of loop. Now let us see what are the possible solutions at t tends to infinity. Okay. Either ns can be infinite, or ns loops onto itself via multiple transformations, or ns is equal to ns via singular transformation. So we form the condition S is P or Q or R. We define P, Q, R. We know that P is not true, Q is not true, so R is the only option. Not P, not Q implies that S is equal to R. So one can conclude that for all elements at t tends to infinity, Ns transforms to 1. Thus the conjecture is true. Now the approach that we have taken is not straightforward, it's indirect. We create sets, we prove that those sets are valid, true, we analyze the properties of those sets, and then apart from that, corollaries that we have established help us create the base to attack the problem, because it is not something that you can attack straightforward. The attack has to be indirect. So I have tried to explain the overall approach towards the solution. It's possible that I might have missed out a few points. If I have not been able to clearly express myself, or you have not been able to understand what I'm trying to say, kindly write down in the comments that this section is not clear, or you find an error in my paper or in the video. Please share in your inputs and I will incorporate that. And if you find the solution to be true, you can recommend others who are interested in this problem or mathematics to watch the video and spread the word. And if there is any publication which is interested in publishing the paper, you find it to be valid, correct, so you can contact me, and let's take it forward from there. Thank you. Have a good day.